This is a short summary for Chapter 7, Part 2. The focus on this part is to derive the laws and to explain the structure of monads and semi-monads. To derive the laws, I begin with intuition coming from using functor blocks, and I formulate the main intuition as saying that this generator arrow means that the value of x will go over items in container C. And if that is the case, then what are the properties of various programs? And I formulate three such properties that seem to be natural. And then I formulate these properties in algebraic notation and also illustrate them using type diagrams. Now these are somewhat complicated combinations of Flatmap, which I denote like this, and Fmap. Is there a shorter formulation of the laws? There is. If we consider the method called flatten, which I denote like this, which is standard in Scala, the connection between flatten and flatmap is that illustrated in this diagram, and it will turn out that flatten only has two laws, and these laws are somewhat easier to understand than the initial three laws here. I notice that we have often the situation when two functions are computationally equivalent. And one of them is a natural transformation and another is a kind of lifting. And they have equations that express one through the other and back. And we had the same situation with deflate and fmap opt in the previous chapter. So here I show a general pattern where a natural transformation with this type signature and a lifting with this type signature are related and they are computationally equivalent, and I give a proof. And I'll also give a proof that the natural transformation will have one law fewer than the lifting function. Now, having that in mind, we now derive the laws for flatten. The three laws are formulated in terms of flatten instead of flatmap. We find that the first law holds automatically. The second law gives this. Now I have introduced a short notation for fmap, which is this up arrow. So this is the function lifted into the functor, and this is the function lifted twice. The third law gives the associativity law for flatten. So I comment also on parametricity, which is that naturality law will hold automatically as long as the function is implemented using a fully parametric function, fully parametric code. I will show with explicit computations that flatten for each of these monads satisfies the associativity law. This is now checked symbolically in my lecture and takes quite a long time. I give examples of a semi-monad that is not a full monad and yet has useful applications. I show code for this. And I also give examples of implementations of flatten that violate associativity. The next topic is a full monad. Now, the full monad has the method pure in addition to Flatmap, and the pure represents an empty context. I explained that monadic composition can be seen as a combining of contexts, and so combining empty context with another context should be a no-op. It should not modify this other context. And if we formulate this requirement in terms of code, we get the two laws, left and right identity. Now, the pure operation also must be a natural transformation. So once this is satisfied, we have three additional laws that are formulated using Flatmap, like this. And I also give the type diagram for each of them. However, we can reformulate all the laws of the monad in a much more concise way, remembering how this was possible for the filterable functors if we used this fmap opt lifting, which had this type signature, and now we have Flatmap that has this type signature. It's quite similar, except we're using a different functor here. Otherwise, it's a lifting of a kind, which is a Kleisli function here with functor s instead of this functor option. So just analogously to what we did in chapter 6, we defined the Kleisli composition, Kleisli identity function, and we then show that reformulating Flatmap laws in terms of the Kleisli composition operation, we get the left and right identity laws and the associativity law. So these are very similar to the laws of ordinary function composition, except we use this Kleisli composition instead of ordinary composition, and we use pure, which is a special kind of function, instead of identity function. So to generalize this, category theory says that the twisted function signatures, which we have seen before, these are called morphisms, and there must be a composition for any two morphisms and an identity morphism defined in some way, so that identity laws and the composition associativity law must hold. And category theory generalizes a lifting to be a map from one category to another, rather than what we have seen before, the functor that we said before. It is a lifting from this to this. So if you think about the fmap type signature, that's a function from this to this. Category theory generalizes this to say that a general kind of functor can be a map of lifting from any one category to another. So for example, from this to this could be, or from this to this. And the laws will still be the same, the identity and composition laws for the functor. So in this way, category theory generalizes what we have seen in filterables and in monads to a single formulation. And I say that endofunctor is what we used to be calling functor, which is that it is a lifting from here, from the plane functions. So for people who already know category theory, this is a very much simplified definition of category that is adapted to programming, to functional programming. So I'm not considering any kind of abstract categories and abstract morphisms. We always consider morphisms that are implemented in code as functions of a certain type. I also show that once you assume that this definition of a twisted function type forms a category, then you can derive monad laws and vice versa. So in other words, now all these monad laws, the 6 laws that we started with, are equivalent to a single statement that the functor S be such that these function types are morphisms in a category with all the right laws of a category, which are standard. And those laws are easy to visualize. They're just identity laws and associativity of composition. So I derive both directions of this equivalence. Now we have seen that there is this identity and composition, which is very similar to semigroup and monoid. So I consider next the possible semigroups and monoids and how to construct them. These are the various constructions, and I show code for them, such as product and disjunction and so on. I should give some non-trivial examples of monoids. Similarly, we can now look at the possible structures of a monad or a semi-monad. Here I give a remark when something can be only a semi-monad or also a monad. So these are constructions that some of them are well known, others are less well known, such as this construction is a free monad. This is very well known, but this is a free pointed, it's less well known. This is the G-shaped tree with G-shaped leaves. That is a semi-monad only. And this is a semi-monad or monad with some restrictions. And I give exercises for this material. There are many exercises in this chapter. It's very long and the derivations are very detailed. I encourage you to go through all of this in detail. It will take you maybe a week or two. And finally, some remarks about various details of what I was talking about in the lecture.